There is a tectonic shift underway in computing. Something so massive, it's reshaping the entire energy industry, computing, and even geopolitics. Let me show you. Last December, it was just quiet farmland. Today, it hosts one of the largest AI data centers on Earth. Close to 1 million AI processors under one roof, pulling up to 2 gigawatts of power. And the most remarkable detail, inside there is not a single GPU. This is the first AI supercluster of this scale built without a single GPU. And this is either the smartest bet in modern AI or the most expensive miscalculation in the history. I have spent more than a decade in semiconductor industry, but nothing prepared me for this. Across the planet, farmland is giving way to data centers. Mother Earth is starting to look like a motherboard. This is rural Indiana, a quiet town called New Carlisle with a population of 1,900 people. Today, it hosts the project Rainier, an 11 billion AI supercluster. Amazon didn't just stumble into Indiana. This was a calculated choice. Vast, affordable land, space to expand far beyond what exists today. And most importantly, the access to power grid that can deliver more than 2 gigawatts of power. The project was announced last year, and somehow it's already operational under 12 months. For something that large and that custom, that's a breakneck pace. And the timing is no coincidence. Right now, the largest tech companies on the planet, Google, Meta, Amazon, and others, are locked in the race to control AI infrastructure itself. Not just the models, but the physical foundation these models run on. Hundreds of AI clusters are racing across the United States, Europe, and Asia. And almost all of them follow the same formula: endless rows of GPUs. But Project Rainier breaks that pattern. It already operates 7 buildings, with planned for up to 30 total buildings on that site alone. What makes it fundamentally different is what sits inside. Instead of filling all these rooms with GPUs, Amazon built the system around its own in-house designed chips, which are integrated in quite a different infrastructure. And that decision changed everything. Economically, technically, and strategically. And this is where all the risks begin. Until now, the rules were simple. Buy GPUs, scale, repeat. The more, the better.
Okay, and so anyways, the more you buy, the more you save.
In the largest AI superclusters, GPUs are now effectively everywhere. Take the world's biggest AI supercluster today, xAI's Colossus 2, in Memphis. It runs close to 1 million NVIDIA Hopper and Blackwell GPUs under one roof. This model is powerful and proven. It's also scaling in a predictable way. But it is showing cracks. Explosive demand has made GPUs the primary constraint. And it got worse as manufacturing delays started to pile up. And actually the bottleneck shifted from chip production to packaging. The interesting part is that Blackwell GPU relies on TSMC's advanced packaging technology, so-called COWOS-L packaging, chip on wafer on substrate packaging. This packaging tightly integrates high-bandwidth memory directly with the GPU on one single massive interposer. That single packaging step has quietly become the true choke point of the AI supply chain. Demand for Hopper and Blackwell systems now exceeds what TSMC advanced packaging capacity can physically produce. As someone who spent years in the industry, seeing what's happening with Blackwell genuinely scared me. Lead times stretched into months. Costs climbed, and not just for the chips, but for everything around them. Many still think NVIDIA is selling GPUs, or graphic cards. In reality, they control the entire AI ecosystem, while actually they sell infrastructure. Server platform like AGX platform, including networking solutions and enterprise software. This means big tech and AI labs were no longer simply buying compute, but buying into an entire controlled ecosystem. When a single high-end rack can approach $3 million, you can imagine what it means to fill an entire data center with thousands of them. At the same time, workloads kept exploding. Models jumped from billions to tens of trillions of parameters. Training cycles stretched across many months. Power demand climbed into the gigawatt range. Suddenly, the performance alone was not the main constraint. Cost and efficiency became just as critical as the raw compute. And with that, competition just changed its nature. Now, hyperscalers are no longer racing to train the best models, but also to control the silicon these models run on. And this is the pivotal moment where the whole trajectory is shifted. Amazon saw it early. Even at their scale, they did not have the control of its own AI infrastructure. It had to be owned, controlled, and optimized from the inside. So the strategy had to change. Amazon decided to build its own silicon, called Trainium. It is so-called ASIC, Application-Specific Integrated Circuit. It's built for a month-long process of training large language models. Trainium circuits are designed for this intense process where large language models are created, refined, and scaled over many months. And you can actually see this on silicon. It's the beauty of ASICs, actually, because you can take the core defining algorithm and literally engrave it in silicon. And that unlocks the efficiency which software algorithms can merely imitate. Inside Trainium 2, you do not find countless small GPU-style cores. You find large number of neuron core wrapped in high-bandwidth memory. At a high level, it mirrors the philosophy behind Google TPU. 2 compute dies, 4 stacks of high-bandwidth memory, and advanced COWS air packaging. All of that optimized for cost, efficiency, and a smooth supply chain. Inside data centers, these chips scale like a root system. Trainium units sit in trays. Trays form servers. Racks connect through Amazon's custom network fabric until thousands of AI processors behave like one colossal machine, spanning entire buildings. According to Amazon, this setup delivers roughly 50% better pricing than comparable GPU-based systems. And that's a big deal. Plus, this custom solution can reduce data center energy consumption by up to 40%. And that is the whole point. Not to outmuscle GPUs on the raw performance. This is still very distant. The objective is more strategic, to control the infrastructure, to tame the cost curve, and dictate the economics. At Amazon reInvent event a couple of days ago, they announced the new Trainium 3 chip, built in 3-nanometer process.
4.4x more compute, 3.9 times the memory bandwidth, and this one is super important, 5 times more AI tokens per megawatt of power. And as a special surprise, I have a rack of our Ultra servers on stage with me today.
And this is where the story pivots, because this project isn't limited by money or silicon. The first battle isn't compute. At this scale, it's power. When you build an AI data center, you are not just stacking servers. You are orchestrating power lines, substations, on-site generation, cooling loops, transformers, and grid stability. When fully built, this site is expected to draw more than 2 gigawatts of power. In a town of just 1,900 people, one AI campus now rivals the power appetite of an entire region with millions of homes. And the local grid was never designed for a machine of this magnitude. The problem was not even the scale, but stability. Massive load pushing the grid to its limits, hovering very close to blackout. Here, finding energy is just a half of the story. Real challenge is keeping it perfectly steady. And that's a fundamental difference, because traditional data centers were built around storage and routine compute, while AI data centers are a different beast. They require extreme performance, extreme compute density. GPUs don't draw power smoothly. They demand jumps up and down in milliseconds. If the supply cannot keep up with these swings, the entire system becomes unstable. And a sudden surge can drop voltage, and in the worst case, ripple through entire halls. And restarting those runs burns millions of dollars in wasted compute. Here, Amazon had to reinvent how the power flows in a data center. In fact, it doesn't flow directly from the power grid to the racks. It passes through a special stabilization system that smoothes out every shock before it reaches the hardware. At Rainier, Amazon deployed a large-scale battery system to absorb power fluctuations. They store energy when demand is low and release it instantly when demand surges. The result is calm, predictable power, feeding hundreds of thousands of AI chips without interruption. And this is where the shift becomes obvious. Hyperscalers are no longer just building data centers. They are literally turning into energy developers. Just like Amazon, along AI campuses, they are funding power plants, reinforcing grids, and investing in renewables. And all of it to lock in cheap, reliable electricity before anyone else gets there first. And at the same time, they're pursuing the second lever of control: designing custom silicon to squeeze as much compute as possible from every watt of power. And this actually defines the next stage of AI development, because the race is no longer about performance. It's about who can engineer a whole system where power, cooling, silicon, and data moves in a perfect lockstep, and keep working as scale moves from colossal to absurd. And if you're enjoying this episode and you care about where the whole computing is heading, subscribe to the channel. And this race at the infrastructure level is reshaping another one, just as critical: skills. We are coming at the end of the year, and AI was one of the most in-demand skills as of 2025, according to the World Economic Forum. And as 2026 approaches, the demand is only accelerating. Yet many people still have not learned it. That's why I recommend you join me for the 2-day AI workshop by Outskill. They're hosting a live workshop this Saturday and Sunday from 10 a.m. to 7 p.m. EST on both days. More than 10 million professionals just like you have already attended this training. From marketers to engineers to founders, and many walked away not just smarter, but with skills they can monetize. And the timing is perfect, because right now they have a special holiday offer, and you can attend this training, which usually costs $395, for free. I highly recommend you to join this training because you will be mentored by AI experts from companies like Microsoft and NVIDIA. Inside these 16 hours, you will learn how to use AI to simplify your daily work. Build AI agents, automate your workflows across Sheets, Notions, and CRMs. Create real-time AI systems you can use for your job, business, or project. You will also receive bonuses worth over $5,000 if you attend both days, including a prompt Bible, a personalized AI toolkit, and a roadmap to monetize these skills. This is your opportunity to step into 2026 sharper, more skilled, and ready to level up your career. Register right now through the link below or scan the QR code here and join their WhatsApp community to stay updated before the training starts. And thank you, Outskill, for sponsoring this episode. Well, securing 2 gigawatts of power only unlocks the next problem. The moment electricity hits the servers, it becomes heat. And the scale is unforgiving. It's roughly 2 gigawatts of heat wrapped inside 4 walls. Now, how do you remove all of that heat? To cool a data center at this scale, it takes millions of gallons of water every day. In extreme cases, it pulls from the same water supply people rely on for drinking and sucks their aquifers dry. Project Rainier stepped straight into that pressure point. It pulls from the local environment in Indiana while operating an AI supercluster with extreme cooling demands. The water problem was immediate and impossible to ignore. And Amazon took a strangely different path here. They designed Rainier to minimize water use as much as possible. They designed it in a way that cooling leans heavily on outside air. From October to March, it uses no water for cooling at all. And in warmer months, water is only used for a few hours per day on average. And it looks almost counterintuitive. To make this work, Rainier relies on massive fan walls and relentless airflow. The system stays in constant motion. But this choice carries consequences. More noise, more power draw, and more strain on the electrical system. In general, water is much better at absorbing and moving away the heat. It's roughly 30% more efficient than air. This means it allows to pack more compute in the same space and lower the energy consumption. This particular design reflects a calculated compromise, a core dilemma at the heart of modern AI. Protect water, but burn more power. Save energy, but strain local water system. Every decision here carries a cost. And a search for new power sources is a part of the answer, but it doesn't erase the core dilemma. But even if you build the best silicon in the world and the best cooling system, still there is one thing that decides everything: the whole system. And a huge role here plays the network. Unlike data centers built around NVIDIA's infrastructure, which lean heavily on optical networking, Amazon chose a different path here. They've built a custom network, which is based on dense copper wiring. Optical interconnects at this scale is extremely powerful. It's allowing for higher bandwidth and more elegant layouts at extreme scale, but it's also extremely expensive. Amazon went for copper for extremely practical reasons. It's cheaper, more familiar, easier to install, and deeply embedded in existing data center infrastructure. Engineers know how to bend it, route it, and scale it fast. But all that copper comes with consequences. AI data centers are very different from typical data centers, because here we are pushing towards extreme bandwidth, like 800 gigabit per second and moving up towards a terabit per second. And here, copper runs into hard physical limits. What used to work in a typical data center over long distances now only works over a few feet. Suddenly, physics pushing back and generates lots of heat. And yet, Amazon stayed with copper, only partially introducing optics for longer distances, and paired it with aggressive cooling techniques and obsessively controlled layouts. The result works, but at the edge, where suddenly every inch of routing matters. This scale of investment we discussed today and this massive scale of build-out only makes sense when you have an anchor customer, someone who would truly benefit from that much compute. Microsoft has OpenAI, a tight partnership that has evolved into a stable multi-billion-dollar revenue engine. For Amazon, this anchor customer is Anthropic. Their Opus 4.5 model is one of the best in the world. Their revenue growing fivefold and approaching $5 billion annually. Amazon has invested roughly $8 billion in Anthropic. And Anthropic has committed to running its flagship models on Amazon's Trainium chips.
If you're using any of Claude's latest generation models in Bedrock, all of that traffic is running on Trainium, which is delivering the best end-to-end response times compared to any other major provider. And that's part of the reason why we've deployed over 1 million Trainium chips already to date. Now, we've gotten to 1 million chips in record speed, and that's because the whole process, we control the whole stack. We can optimize end-to-end how we roll it out, and it allows us to move even faster.
And this is where the strategy turns both very powerful and dangerous. What's interesting, this Trainium 3 chip was co-designed in close collaboration with Anthropic team. In practice, their model architecture shapes the silicon. The silicon, in turn, accelerates the models. And this is the true edge and the true beauty of co-design, which unlocks this efficiency which general systems can never reach. Until recently, this level of co-design was almost exclusive to Google and DeepMind through TPU. TPU is Google's in-house design chip, tensor processing unit. Google's TPU is one of the purest expressions of what an ASIC or a specialized AI accelerator is meant to be. Gemini 3, one of the best models on the planet, runs on Google Cloud powered by these chips. And now everyone wants it. Google is selling it to external customers. xAI and Meta are circling. Anthropic is placing massive TPU orders. So why all the top AI labs are lining up for these chips? Because GPUs designed for versatility. Their power is flexibility and raw peak performance. While Trainium and Google's Ironwood TPU and ASICs in general, they're intentionally sacrificing this to maximize efficiency. While currently, everyone is caring less and less about these benchmarks and more about one brutal metrics: performance per dollar. And this is where the story turns. Because Amazon isn't just scaling compute, it's betting on delayed return. But can they repeat the kind of success Google pulled off with TPUs? Trainium 2 chips still have to prove itself at this massive scale, and its success tightly depends on the system, and on the software, and on success of Anthropic. This is the tension at the heart of Rainier. Now, if we zoom out and look at the bigger picture, Rainier is part of a much larger build-out. Amazon is committing another $15 billion to Indiana alone, which means more land and over 2.4 gigawatts of new capacity. Across the United States, Amazon is investing over $100 billion in AI infrastructure in 2025 alone. And these new sites will power enterprises and AI labs like Anthropic, running at industrial intensity. Some of them will run on Trainium chips, while other sites will load up on GPUs for flexibility and immediate demand, because customers want options. Amazon runs basically both tracks in parallel, custom silicon and GPUs. And they are not betting on a single future. They're letting the market to decide which one survives. Everyone is talking about AI bubble. But the real problem is structural. Anthropic spends heavily on Amazon Cloud. Google also invested another $4.5 billion in Anthropic. And Claude now runs across both ecosystems, Amazon Trainium chips and Google TPU infrastructure. It's a capital loop. Big tech injects money into AI labs. AI labs spend it on compute. New models need more compute, and it drives even more chip sales. The danger is that this cycle repeats faster than the actual profits can catch up. And that's pretty exciting, because now this story is not just about custom silicon and building better chips. It's about the control over the most scarce resource in the whole AI infrastructure: power. And here, Amazon's strategy is very strong. At first, they aim to build more efficient chips. But the real strategy is a full vertical control: chips, software, data centers, energy sourcing, and renewables. Here, the clearest signal is in Pennsylvania, where Amazon acquired a 960 megawatt data center campus right next to the nuclear power plant. Actually, the data center is connected straight to the power plant, and this gives Amazon access to almost 40% of all the electricity the plant produces. And this is a very powerful strategy, because you cannot simply drop a data center anywhere. Power for this scale must be engineered years before the first server turns on. That is why Amazon is moving so aggressively and investing a lot in nuclear power plants, large-scale battery systems, and renewables. More importantly, it places all its data centers beside stable base load power. Ohio, Mississippi, Pennsylvania. New sites keep switching on. These are not just data centers. This is a distributed power grid spanning across the entire United States. And the future winners in AI will not just be the ones with the smartest models. It will be the ones who secured power, land, and silicon first, and then align them together in one system that can scale without becoming too expensive to sustain. And this is also a super interesting moment where AI hardware stops becoming a one-vendor story. We discussed Amazon and Google, but also Meta is no longer just buying chips. It's designing them with the help from Broadcom. Microsoft is also following the same arc. And AMD is closing much of the performance gap while steadily improving its software stack. We constantly see a wave of new AI accelerators being announced, and just as quietly, many of them disappear. Not because the idea is wrong, but because the bar is too high. Because it is not just about the chips. If you cannot build a system which is meaningfully faster, cheaper, and more efficient than what you can already buy off the shelf, then why to build it at all? Tesla Dojo is one example. Beautiful moonshot. Years of work, a lot of inventions, world-class team, yet this year it was shut down. Startup GraphCore burned $700 million building custom AI silicon, betting on the wrong algorithm. Still, looking at success, huge success of Google custom silicon, and the general hyperscalers' push for designing in-house chips, it's quite clear that the future will belong not to a single vendor or a single architecture. It will live across an ecosystem with GPUs for flexibility, custom accelerators for efficiency, and advancements in silicon photonics, which will allow us to build better systems. Across the planet, farmland is giving way to data centers. Cornfields are becoming compute fields. Land once measured in harvests, now measured in gigawatts and exaflops. 10,000 years ago, the first great revolution taught us humans how to feed ourselves. This one is teaching us how to feed machines. And everything that follows will depend on that choice. If this episode sparked your curiosity, you will definitely enjoy this one, where I take you with me inside this secret microchip factory, where you can see with your own eyes the technology of the future, which is coming to all your devices after 2032. Or watch this episode where I break down what it takes to build a $50 billion microchip factory from scratch. And I will see you there. Ciao.